Okay, welcome back. This is supplemental material for the assignments. I'm really happy to see you here. Okay, we're going to talk about the traveling salesman problem, which is a really challenging, optimization problem. So this is a challenging assignment. And we're going to review some of the concept here. And some of the things that we do in these assignments is actually simplifying your life. And I want to go over some of them because you can actually use some of these things on other assignments as well. So remember, what a traveling salesman problem is that you have a bunch of points. And what you want to do is to find a tour which is visiting every one of these points exactly once, okay, and minimize the overall travel distance, okay, or cost, whatever. Okay, so this is a beautiful tour that you see on that site. It's a tour doing 0, 4, 8, 9, 5, and so on, okay? And so an interesting point here is that you can essentially see, a tour as a permutation of all the vertices, okay? And this is nice because, it basically tells you how you can actually, output a solution. And you can also think that this is a good representation, but it may not be, right? So this is one of the things that we'll need to discuss at some point. Okay? So, in this particular assignment, we are going to focus on a very specific class of traveling salesman problem. They are going to be Euclidean. It's a metric space, so computationally these problems are easier. And also they have a big, very nice features that I will tell you about in a moment. Okay? So it will help you tremendously. Actually, the fact that we are looking only at Euclidean TSPs. Okay, so in a Euclidean TSP, essentially every one of the points is a coordinate, as a coordinate. Okay, so you see, for instance, that point 0, vertex 0, as coordinates 17 and 27, and this is essentially going to be the input of your problem. Okay, and once you have that, we'll be able to compute the distance between any of these 2 points, and that's going to be the distance that we'll be using when we are trying to evaluate the length of a particular tour that we are trying to compute. Okay, so in a sense, the only thing that the input will be concerned with is giving you these coordinates for the point, and from that we don't have to compute this big, give you this big distance matrix. You can actually compute it yourself. Okay, so essentially, once you want to find out what is the distance between 0 and 4, you will use the formula that you see here, okay, which is basically actually you see the actual values at the bottom. You'll take the x coordinates of the 2 points, okay, subtract one from the other, square it, do the same thing for the y coordinate. Square it, sum them, and then take the square root of the whole thing. And that basically is giving you the distance between, let's say, point 0 and 4. Okay? So what you do is you take 17, subtract 42, square that. You take, 27 and subtract 56, square that, and take the overall square root, and that gives you the distance of 38.288, which is the distance between these 2 points, the Euclidean distance between these 2 points. Okay, so what is important here is that we will only give you the coordinate, of the various vertices, and you can compute easily using this formula the distance between any pair of vertices. Okay. And so essentially, this is summarizing what I told you. The only thing that we really need to tell you is what are the coordinates between all the vertices, and that's going to be the input of your problem. From there, you can deduce everything else. Okay? So this is a formulation of the traveling salesman problem, where you see the objective function computing all these distances between all the various cities in the tour. Okay? So we are basically modeling here. Okay, the tour as a permutation of the vertices. Okay, this doesn't mean that you have to model your problem like this. Okay, so in these supplemental materials, sometimes we use model. We make no guarantee that these are good models. Okay, it's probably not a very good idea to recompute all these things all the time. Okay, so you may think of other representation. It may also not be a very good idea to model the problem as a permutation. Okay, so some technology may not like that. Okay, and some may. Okay, so in a sense, every time we put a description of the problem, we typically make no guarantees whatsoever on whether it's good or not. It's just a particular formalization of the problem. Typically, the Python script may use that formalization to give you a basic solutions. But, don't make any assumption that this is a good formulation. Don't be, misled by the fact that we are putting that formulation. It may be completely crappy from a computational standpoint. It's just very convenient for stating the problem. Okay? So in a sense, what I need to tell you now is essentially what the input and output should be for this particular assignment, okay? So the input is very simple, okay? So I'm telling you how many points there are, okay? And some of these problems, may have, 50 points. Some other ones will have many more, okay? And then for every one of these points, we'll basically give you the x and y coordinates, okay? And as I told you, using the formula that you have seen before, we can compute the distance between any 2 points, okay? The output, is basically the format that we are using systematically, okay? So you have to specify the objective function, whether you have, proved optimality or not. And then in this particular case, we ask you to put, a sequence, which is a permutation of all the vertices, okay? So this is basically describing the tour that you have if you connect the last one to the first one, okay? So in a sense here, we ask you the permutation at the end. Once again, it doesn't mean that your modeling has to use that, okay? You can use a modeling where the decision variables are very different, okay? But at the end, you will have to transform those decision variables into something which is a sequence, okay? This is a particular example, okay? So you basically see here inside the input 5 vertices and the various coordinates. The first point is 0, 0. The second one is 0, and 0.5, okay, and so on and so forth. And then you see a solution here which has a length of 5.2, and the tour is 0, 4, 1, 3, 2, and so back to 0 at the end, okay? And so essentially you see a permutation of the vertices here, okay? You see the value of the objective function. Okay, so that's what you need to output. Okay, obviously, once again, and I will repeat that ever and ever, forever, is that we can obviously compute the value of the objective function for this permutation, and that's one of the things we'll check in the script. Okay, so now one of the really important feature of the traveling salesman problem, okay, and especially the Euclidean traveling salesman problem, and the fact that we are actually giving you this coordinate, is the fact that you will be able to visualize what you are doing, okay? So you can use the location of these points, in the plane to actually see, to actually visualize your tour. See where they are, visualize your tour. So this beautiful output that you thought was very great, if you try to visualize it, this is what it gives you. And this is pretty crappy, right? So as soon as you have edges that are crossing each other, bad news, okay? So that means that you are very far from optimality, okay? So one of the things that you want to do in this particular assignment is visualize how good your tour is when you are using different techniques. And that will help you a lot because it will identify bottlenecks, things that your algorithm is not doing well, things that you should focus on, and things like this, okay? Now, the TSP is very nice for doing this, but in most of the assignments, so this is something that I highly recommend. If you can build a visualization to see how your algorithm is doing, modeling various aspects of the problems, the objective functions, the various aspects of your algorithm. If it's a constraint programming algorithm, how much it prunes. If it's a local search algorithm, what is the sequence of solutions that it gets you, how fast, it goes down, whether it stays at the same place many times, okay? Things like that. If you are using mathematical programming, what is the relaxation? How good is it, okay? So these things you want to visualize because they will give you a lot of insight on your algorithm. So, and I'm speaking from experience. I spent hours and hours looking at a screen of, data. And sometimes a simple visualization will give you, the ha-ha, the wow factor that you need to actually understand what your algorithm is not doing well, okay? So this is a good example here. It's actually pretty easy to do. Build this visualization. It will help you. And this is obviously, if you see that, you say, this is a pretty nice tool, right? And so assignment tips, okay? So there are a lot of assignment tips on this particular problem. There are a lot of things you can do. Okay, here are a couple of ones. Okay, so first, if you implement local search, one of the things you need to focus on is how quickly can I explore the neighborhood. Okay, so we can have a lot of very sophisticated neighborhood or a lot of very simple neighborhood, but we may want to explore them and they may be very large. How do you do that very quickly? Okay, so this is a key aspect of the TSP. Symmetries and dominance, there are plenty in these problems as well. You have to think about them, okay? Can you actually avoid, exploring subpaths and things like that that are dominated by others or they are symmetrical to others? Try to think about that. One of the things in this problem as well is that essentially every city, if you're visiting cities, can be connected to any other city, okay? Every vertex can be connected to every other vertex. But do you need all of them? Okay, so think about it. You are trying to do a tour of the United States? Are you going to connect Miami to Seattle? You're trying to do a tour of Australia. Are you going to connect Perth and Brisbane? Okay, think about them. Okay, so are you going to do that? And also, can you prove that you don't need these edges? Okay, so that's one of the things that you can think about. If you do complete search, think about the various ways you can actually compute lower bounds. There are many, many ways of computing lower bounds, different trade-offs between, speed of computation and quality of the lower bound. And then, as I said, visualize. Look at the solution. Look at what your algorithm is doing. Whatever the algorithm that you are going to do, sometimes you will be surprised at what it does. And it may be useful to actually visualize to see some of the aspects that you can improve. Okay? Have fun. This is an amazing assignment. Okay? And people have, as I told you, this is one of the most studied problems in optimization. It's very interesting that you actually try, some of the techniques on these problems. Although it's very specific, a lot of different techniques in different fields, have been applied to this problem. Okay, good luck.